Good morning, everyone. Welcome back to Machine Learning Summer School 2021. I'm Chun-Yi Lee, and I'm an assistant professor in National Yang Ming Jiao Tong University. Today, we are very happy to have Professor Chun-Yi Lee as our speaker, and he will talk about fundamentals and applications of deep reinforcement learning. Professor Lee is an associate professor in the Department of Computer Science in National Tsinghua University. Professor Lee's research focuses on a number of areas, including deep reinforcement learning, intelligent robots, computer vision, and parallel computing systems. And he has published a number of research papers in major machine learning conferences, including NeurIPS, CVPR, ICOR, ICML, and more. Professor Lee has made many great achievements. Just to name a few, he has led his lab members to win several prestigious awards from a number of worldwide robotics and AI challenges, such as the first place at NVIDIA Embedded Intelligent Robotic Challenge in 2016, the first place of the world at NVIDIA Jetson Robotic Challenge in 2018, the second place from PIC Challenge at ECCV in 2018, and the second place of the world from NVIDIA AI at the Edge Challenge in 2020. And if you have any questions, please type in the chat box and Professor Lee will take the questions later. Professor Lee, please start.
Hi, welcome to the talk. Hi, welcome. Hi, welcome to the talk. Today we are going to talk. Hi, welcome to the talk. Today we are going to talk about the fundamentals and applications of deep reinforcement learning. And I'm the presenter, Chun-Yi Lee. I am an associate professor of computer science, National Tsinghua University. My research interest lies in intelligent robotics, deep reinforcement learning, computer vision for robotics, as well as virtual to real learning for robotics. I founded ELSA Lab, which is dedicated to deep reinforcement learning researches and computer vision technologies, especially for intelligent robotics and autonomous agents. Currently, we are very welcome for full-time research assistants, PhD students, and master students, as well as undergrad students. This is the agenda of today's talk. We will first talk about the background materials of reinforcement learning, and then we will talk about the deep reinforcement learning techniques that are commonly used by researchers. And then we will talk about the exploration techniques, which is very important for training agents. And finally, we will talk about robotic applications using deep reinforcement learning techniques that we have discussed. Okay, let's begin with the basic concept of Markov decision process, which is very important for reinforcement learning. Markov decision process is usually abbreviated as MDP, which consists of an agent and an environment. The agent interacts with the environment for every time step. At each time step t, the agent observes the current state of the environment st, performs an action at according to its policy pi. The environment then transits to the next state st plus 1. During this process, the agent may receive a reward signal r, and which can be good or bad for different actions. The agent keeps interacting with the environment for many time steps until a terminal state. The total length of the interactions is called an episode. During the training process, the agent learns and updates itself for a number of episodes. The final objective of the agent is to maximize the expected sum of the rewards. This sum of the rewards usually comes with a discount factor gamma. The value of gamma determines how much the reinforcement learning agents cares about the rewards in the distant future relative to those in the intermediate future. In theory, it is for convergence proof. In practice, it is usually to prevent unrealistic planning, since we do not necessarily want the agents to be myopic or care about overly long-term rewards. So, given the above formulations, we would first like to know how does reinforcement learning solve MDP. Remember that different actions performed by the agent lead to different rewards, and the actions to be performed by the agent for each state is governed by the policy of the agent. In order to solve MDP, the goal of the agent is to find an optimal policy pi star such that the total accumulated reward G can be maximized. The policy of the agent can be either deterministic or stochastic. A deterministic policy directly decides an action for each given state, while a stochastic policy samples an action according to a probability distribution. Now we want to know how to find such an optimal policy pi star. Reinforcement learning has been investigated for many decades and can be broadly categorized into three different categories: value-based reinforcement learning on the right-hand side, policy-based reinforcement learning on the left-hand side, as well as actor-critic, which sits in the middle. There are several other techniques that combine methods from different categories and leverage the benefits from them as well. No matter which categories we use, the ultimate goal is to look for the optimum policy that performs best in an environment. So what are these three categories? We will now briefly introduce each of them one by one, and begin with the policy-based method. In policy-based reinforcement learning, we directly learn the policy pi, which may be parameterized by a set of parameters theta. The policy may lead to different expected total rewards when the agent starts from a state in an environment. We now formulate an objective function j of theta, which defines that the expected total return achieved by the agent's policy. By this formulation, we actually correlate the parameterized policy with the return of the agent. If the policy is good, the expected total return will also be good. So how do we get a better policy? The recent advances in deep learning tell us that we can use gradient updates to improve the policy. If we can take the gradient of j of theta, we can get the equations shown in this page. This is called the policy gradient. As long as we can improve the policy along the directions pointed by the policy gradient, the policy may be gradually enhanced better and better, and may finally reach the optimum one. After the training process, the action is then sampled using the trained policy. The second category of reinforcement learning is value-based method. Different from the policy-based reinforcement learning, value-based reinforcement learning focuses on learning of the value of a state, or the value of a state-action pair. These values represent the possible expected total return under the given state, or the state-action pair. Learning the values allows the agent to tell which state or state-action pair is better to go. In other words, if a certain state or a certain state-action pair seems promising, the agent should move toward them, since they may be better for outcomes. We usually call the value of a state-action pair the Q function. Q function is also usually parameterized by some set of parameters in recent deep learning methods. Since we do not know the Q values of each state action pair, the agent has to learn during the training process. Learning a better Q function is the core of value-based reinforcement learning. QLearning is a popular method for learning a Q function, which has been investigated for many decades. The main idea of QLearning is to compare the difference between the sum of the intermediate reward plus the estimate of the Q value of the next state with the estimate of the current Q value of the current state. This is called the temporal difference learning. There are many other ways for estimating the Q values, such as Monte Carlo methods, distributional methods, and so on. If the Q values can be accurately modeled, the agent can move toward to a better state that has higher Q values in an environment. So, what's the difference between QLearning and policy gradients? QLearning aims to learn the Q values of each state action pair and is an off-policy algorithm. So what is off-policy algorithm? Off-policy algorithms are methods that allow us to use the training data generated by any arbitrary policies. Therefore, the training samples for training the Q function do not have to come from the data collected by the agent, but can come from the data collected by other ways, which can be from some other agents or human-prepared data samples. This is the concept of policy learning. On the other hand, policy gradient is an on-policy algorithm, which means that the training data is collected from the current policy of the agent. Different from off-policy methods, on-policy algorithms require the agent to collect data, use the data to update itself, and continue this loop again and again. The last category is called the actor-critic method. The actor-critic method combines the policy-based and the value-based methods and learns both the policy function and a value function. The policy function is updated using the policy gradient method we just introduced, while the value function is trained using the QLearning method to learn the value of a certain state or a certain state action pair. These two function estimators are usually trained together, interactively improve each of them, and finally, both of them will become better and better. In the beginning, the value function estimator provides some kind of value estimates for the policy estimator to learn. The values estimated by the value estimator may not be accurate initially, and thus the policy gradient may not be effective enough. However, as the training process goes, the agents may explore more and more states and actions in the environment, enabling the value estimator to make better estimations. In this way, the policy estimator itself will also gradually improve itself based on the values provided by the value estimator, and eventually become the optimum one. Therefore, actor-critic is very effective and has been adopted in many recent reinforcement learning methods. So now, based on the background materials we just introduced, we will then move on to discuss the concepts of deep reinforcement learning and some popular approaches that have been used in the literature. Why do we want to use deep reinforcement learning? Traditionally, people may use a single-layer neural network to model either the policy estimator or the value function. Such an approach is effective, however, may fail for some complex tasks, such as those using images as the agent's input. For example, in order to play the Atari game displayed in this slide, the agent has to be able to take into account all of the pixels in an image. If the image size becomes larger, the computational overhead will also become larger. This is called the curse of dimensionality, which means that when the input space is extremely large, it may form a high-dimensional state space. Such a large space will make both the policy and the value difficult to learn. As a result, simply using the pixels as the input may not be an effective way if we want to process the inputs that come from images. Moreover, if we want to apply reinforcement learning to applications such as game playing or self-driving cars, some more complicated model architectures will become necessary. Now, this slide shows the basic concept of deep reinforcement learning. This is very similar to the figure we just shown previously. As you can see in this image, the agent is actually modeled by a deep neural network. The deep neural network can be constructed by multiple fashions, which can consist of different styles of convolutional neural networks, recurrent neural networks, fully connected layers, activation layers, and so on. Integrating neural networks into the agent allows it to abstract the observations and states provided by the environment into meaningful higher-level representations. This can enable the agent to better understanding the environment and perform actions better. This concept is first introduced by DeepMind as a research paper titled Human Label Control through Reinforcement Learning. In this paper, the researchers are able to play Atari games by directly taking raw images as input. Some of the experimental results are even able to surpass human label performance. Now, let's discuss some of the famous deep reinforcement learning algorithms that are popularly used by the community. We will first discuss DeepQ network, which is the one introduced by DeepMind we just mentioned and is proposed for discrete action space. Then, we will talk about deep deterministic policy gradient, called DDPG, and actor-critic-based method that is proposed for continuous action space. We will also introduce a synchronous advantage actor-critic, called A3C, a distributed method that is able to train the agent using only CPUs instead of GPUs. Finally, we will briefly cover the trust region policy optimization and maximum entropy reinforcement learning, which are more advanced but very effective in recent deep reinforcement learning research works. Let's first begin with DQ1. DQ1 is a pioneering work that combines deep neural networks with Q function estimation. DQ1 is based on the formulation of QLearning. As you can see, the objective function shown in this slide is very similar to that of QLearning. However, DQ1 is different from QLearning in two aspects. First, DQ1 introduced the concept of target network. The target network is mainly used in the target return part, which consists of the intermediate reward and the Q value estimate of the next state. The target network is parameterized by another set of parameters, annotated as theta minus. It is updated by the QLearning regularly for every certain period of time. Rather than directly using the learning Q network, the use of the target network allows the return target to become more stable, since the values estimated by the target network do not change frequently. This invention allows deep neural networks to be combined with QLearning successfully, which have long been a difficult challenge. Another contribution of DQ1 is the introduction of the experience replay buffer, which is used to store the state transitions experienced by the agent. When the agent explores the environment, those state transitions are stored into a buffer space and are extracted for training the Q functions later. This invention allows the data samples collected by the agents to be effectively used, since they are not thrown away and wasted. Due to the invention of the experience replay buffer, the agent can leverage all of the state transition experiences and can thus improve the Q function estimators more effectively. Later on, people extended the concept of DQ1 to continuous action space. DQ1 was originally proposed for discrete action space, and as we have discussed before, DQ1 was first used for playing Atari games. However, if we want to extend the concept DQ1 to continuous action spaces, such as robotic applications of self-driving cars, some modifications are inevitably necessary. DDPG is a pioneer to introduce deep neural networks to the continuous action space. DDPG adopts an actor-critic architecture which both learns function approximations for the policy and the Q functions. Different from policy-based method, the policy approximator changed slightly such that it does not output the probabilities of the discrete actions. Instead, the policy approximator takes the current state as its input and outputs a continuous action directly. Similar to DQ1, DDPG also adopts the concept of the target network and the experience replay buffer. As a result, both DQ1 and DDPG are of policy reinforcement learning methods. In order to accelerate the training speed, some researchers later proposed a method called asynchronous advantage actor-critic. This is also called A3C. A3C is also an actor-critic based method. However, it differs from DQ and DDPG in that it adopts a distributed training fashion. As you can see in this figure, A3C allows multiple agents to learn together. Each agent interacts with a copy of the environment and accumulates gradients. After a certain period of time, or if a certain criteria is satisfied, the accumulated gradients are sent back to a central global network and updated. These updates are performed asynchronously, which means that different agents send back the gradients without the need to sync with the other agents. After the global network is updated, the new set of parameters for the function approximators are sent back to the agent. The entire framework continuously updates in this fashion until the convergence condition is met. It was reported that using this distributed training fashion, A3C is able to achieve a faster training speed using only CPUs instead of GPUs. There is a variant of A3C called Advantage Actor-Critic. This is also called A2C. In A2C, before the agents update the global network, they need to synchronize by a coordinator. Researchers have shown that A2C sometimes is in par with A3C and is also widely adopted in different deep reinforcement learning research works. Both A3C and A2C are on-policy learning methods. Now, we briefly talk about some more advanced reinforcement learning methods. One of the popular methods is the trust region policy optimization, which we call TRPO. TRPO is a method for enhancing the traditional policy gradient methods. In traditional policy gradient method, the policy approximators are updated by policy gradients, which may sometimes bring negative effects on the learning process of the policy approximator. This is because the scale of the policy gradients may sometimes overly large, causing the parameters to be deviated from the local optima. In order to mitigate this problem, TRPO and later a method called Proximal Policy Optimization Algorithm, which we call PPO, are proposed to restrict the scale of policy gradients to a certain range. The detailed derivation is very complicated. However, the main concept of them is to compare the current policy and the previous old policy. The spirit is that the policy gradients have to be able to enhance the objective function. However, the current and the old policy should not differ too much. The differences, measured by the KL divergence of them, should be within a trust region, which is denoted as delta on this slide. As long as the policy gradient update conforms to these results, we can somehow assure that the policy updates will less likely to cause negative effects. Another popular branch of deep reinforcement learning methods is the maximum entropy reinforcement learning. The concept of this method is quite popular in recent deep reinforcement learning research works, where one of the famous approaches is the soft actor critic, which we call SAC. As you can see in this slide, and as we have discussed before, the standard reinforcement learning method aims to find an optimum policy that maximizes the cumulative rewards. This method, however, is sometimes not effective enough, since it is not able to allow the agent to explore the environment effectively and efficiently. In maximum entropy reinforcement learning, the objective of the optimum policy is further extended to contain two terms. As shown in this slide, it consists of the original expected return, as well as another entropy term that aims to encourage the entropy of the actions for each state to be as high as possible. In other words, the agent not only has to maximize its total return, but also needs to attempt adjusting its policy so as to increase the entropy of the actions. A higher entropy of actions means that for each state, the probabilities of different actions should be similar. The agent has to learn to balance between these two terms such that it can leverage the entropy of the actions to explore the environment while maximize the total return of itself. This concept is also usually called exploration versus exploitation, which we will discuss more in the next part of this talk. Okay, now let's move on to discuss why exploration is so important for deep reinforcement learning. In the era of deep reinforcement learning, researchers have found that it is extremely data inefficient. For instance, in order to train a DQ1 agent to achieve human-level performance, more than 200 million of data samples are necessary. This is way much more than other domains of researches that rely on deep neural networks. deep reinforcement learning differs from other domains of supervised learning, which usually comes with ground truth annotations of training data. For example, when we want to train a deep neural network for computer vision applications, we can rely on famous training data sets such as MNIST, Cypher10, ImageNet, and so on. These data sets allow the training of deep neural networks to be efficient and effective. However, in deep reinforcement learning, the training data samples are collected by the agent itself. In other words, the quality of the training data is all determined by the agent. If the training data quality is not good enough, the agent may not be trained well, and thus may lead to unsatisfactory performance. To enhance the training process of the agent and improve its performance, a good set of training data samples have to be explored and collected by the agent itself. So now, why the quality of the data samples are important. Remember that reinforcement learning algorithms can be either off-policy or on-policy. In off-policy reinforcement learning algorithms, the data samples can be collected by some other policies, or be prepared by human beings. These off-policy data samples, in the settings of DQ1 and DDPG, are stored in an experience replay buffer, and are extracted for updating the function approximators during the training process. For on-policy learning algorithms, such as A3C, TRPO, and PPO, the data samples are collected by the current policy of the agent. If the policy cannot allow the agent to collect more diversified states and actions in the environment, the data samples will be very similar and may cause the function approximator to degrade in terms of its generalizability. In order to collect useful data samples for the agents to learn, in the past years, researchers have devised a number of so-called exploration techniques to encourage agents to explore the environment, such that the chances of obtaining good data samples can be increased. Let's take a graph here for explaining why exploration is so important in reinforcement learning. In this figure, circles represent different states, while the edges represent the transitions. The agents start from S0 and may proceed with two paths. The path on the right-hand side is shorter and comes with a reward of 1. On the other hand, the path on the left-hand side is longer and may have a very good reward of 10 at the end when transitioning from S4 to S7. However, the intermediate transitions on the left path does not have any reward. Here comes the question. Do we want the agent to be satisfied with the suboptimal solution for the right path, or learn the optimum policy to go the left path? Let's take a look at this modified figure. If the agent does not attempt the unfamiliar actions, it will not be able to find the potential rewards in this graph. There may exist some other states following S0, which we do not know until the state transition is experienced. On the contrary, if the agent remains trying all the actions at S0, it will not be able to go deeper to find the optimum policy. Therefore, balancing exploration and exploitation is necessary and crucial. This is called the exploration versus exploitation dilemma. If no exploration is attempted, the data samples and thus the state transitions experienced by the agent is limited. On the other hand, if the agent does not do any exploitation, the knowledge will not be used to improve the function approximators of the agent. Since a number of exploitation techniques have been discussed by the deep reinforcement learning method mentioned previously, we will focus more on the exploration issues here. Here, we further illustrate two challenging exploration issues that are commonly faced by reinforcement learning researchers: the sparse reward environment and the deceptive reward problems. In a sparse reward environment, the rewards are extremely difficult to obtain and experience. The rewards are hidden in deep states, which are typically hard to visit. If no exploration technique is used, in most situations, the agent may just stay locally, wandering around without obtaining any useful information. This may cause the value function approximator difficult to learn because no reward signal is available. On the other hand, deceptive rewards are also common in many environments, where small values of rewards are easily obtainable and cause the agent to stuck at low states. The agent may think that low states are good enough and does not want to attempt the deeper path due to the shorter zero intermediate reward. In such environments, exploration is also very important. We need to encourage the agent not satisfied with the current state, but go to others that have not been tried yet. So, the main focus is to know how to explore. In the previous slides, we have discussed several exploitation techniques where different reinforcement learning algorithms rely on different optimization techniques to improve the policy approximators or value approximators. However, how do we practically encourage our agents to explore different states and actions in an environment? In the following slides, we will visit some of the common approaches adopted by the reinforcement learning community. Now, I would like to move on to discuss several exploration strategies. These strategies are commonly used by many reinforcement learning algorithms, and as we have discussed before, we want to encourage the agent to visit as many novel states as possible and attempt unfamiliar actions for different states. These techniques are used such that the agent can leverage the experiences from those states and infer a better estimation of the values of them. Several famous contemporary exploration strategies are listed here and will be discussed in the later slides, which cover from Epsilon greedy exploration, noise-based exploration, entropy-based exploration, curiosity-based exploration, diversity-driven exploration, never give up, and go and explore. There are still many others not listed here, but in this talk, I would just like to give you some insights how these exploration techniques are doing. You are definitely encouraged to search for more and probably design a new one by yourselves. The challenges commonly faced and have to be solved by exploration techniques include the latency for convergence, the sample efficiency, as well as the difficulty of implementation. So, when designing an exploration technique for an environment, remember to take them into consideration. Let's first talk about the former three exploration techniques. First, Epsilon greedy exploration technique is adopted in many reinforcement learning algorithms. It is effective for many environments and is simple for implementation. The main concept of Epsilon greedy exploration is to add some randomness to the actions performed by the agent during the training phase. For most cases, the agent performs actions according to its policy. However, with a small probability epsilon, the agent may perform the other actions that are not the same as its policy. Therefore, the behavior of the agent may have some randomness, allowing it to have chances to visit different states and not constrained by its own policy. The Epsilon greedy exploration technique is adopted by DQ1 and many other reinforcement learning algorithms. The entropy-based exploration technique is based on the concept of maximizing the entropy of the actions for each state. The entropy term aims to enlarge the chances of performing different actions such that the agent can attempt different states. The entropy term can be added to many different locations, such as the losses or the return part. Similar to the Epsilon greedy exploration technique, the entropy-based exploration technique adds some randomness to the behavior of the agent. For DDPG, a technique designed for continuous action space, as we have discussed, introduces noises to encourage the agent to explore different states. The noise turn can be designed in different fashion, but the core spirit is to allow the final outcome of the action of the agent to be slightly different from what it expects. This way, the agent may be directed to different states by the noise turn and explore them accordingly. Okay, now there's another approach that leverages noises to encourage exploration, which is called the noisy network, presented at International Conference on Learning Representations in 2018. The concept of this work is to add some randomness directly to the weights of the neural networks by introducing noises. These weights are modeled with their own means and variances, and the actual weights used are sampled using the means and variance predicted by the network. This way, the behavior of the agent will be different each time due to the randomness of the parameter space. Such a randomness may cause the agent to try different actions during the training phase and thus allow it to collect more diversified training data. In 2018, there was another work presented at International Conference on Learning Representation, which also introduces noises in the parameter space. The method is concurrent to the previous one and leverages noise injection to the parameters of the policy approximator to encourage exploration. The noise is injected at the beginning of an episode and remains fixed during that episode. By perturbing the parameters, the policy approximator generates slightly different behaviors and thus is able to increase the chances of visiting different states and actions that the agent has not visited yet. Now let's move on to another work that was presented at NeurIFS 2018, which is called Diversity-Driven Exploration. The concept of diversity-driven exploration is slightly different from the method we just discussed. In diversity-driven exploration, the agent has two turns in its loss function to be optimized. The first turn is the regular loss function, which may come from DQ1, DDPG, A3C, as well as other reinforcement learning algorithms. The second turn is called the diversity turn, which is subtracted from the optimality loss turn to increase the diversity of the current policy from the previous ones. The main idea of diversity-driven exploration is that by encouraging the current policy to deviate from the previous ones, it may probably have more chances to visit states that have not explored yet. The diversity function can be implemented in different fashions, which can be cosine similarity, L2 distance, or KL divergence. The parameter alpha that is multiplied with the diversity turn decreases over the training process, such that the diversity turn becomes less important as the agent's function approximators converge. This method has been applied to many different test environments, such as Atari games and Mujoko, and has been proven very effective. Next, we would like to proceed to the curiosity-driven exploration and introduce the concept of intrinsic rewards. As we have discussed before, the objective of reinforcement learning agents is to maximize the rewards from the environments, which we call external rewards or extrinsic rewards. In sparse reward environments that we mentioned before, the external rewards are very difficult to obtain and thus may cause the agent to fail easily. The concept of intrinsic rewards can, under such conditions, be used to encourage the agent to explore the environment and potentially find out the true external reward signal. Intrinsic rewards differ from external rewards in that they are generated by the agent rather than provided by the environment. As a result, the agent needs to have a way to measure the novelty of a state, such that the intrinsic reward is high when the state is first visited, and the intrinsic reward gradually decreases when the state is visited many times. As long as the intrinsic reward signal has such a property, it can be used to encourage the agent to explore more novel states. Curiosity-driven exploration is an approach that leverages intrinsic rewards to encourage exploration. In order to measure state novelty, it proposes an intrinsic curiosity module, which we call ICM, containing a forward model and an inverse model. ICM takes the tuple of state transitions as its input, which consists of the current state ST, the next state ST plus 1, as well as the action actually performed by the agent. The two states ST and ST plus 1 are first processed by an embedding network to generate their embeddings phi of ST and phi of ST plus 1. The inverse model then uses these two embeddings to guess the action performed by the agent. The gradients of the inverse model is used to train the embedding networks such that the useful features from the states can be extracted. The forward model, on the other hand, is used to generate the intrinsic reward. It uses phi of ST and the action AT to predict the embedding of the next state phi of ST plus 1. It is then compared with the true next state embedding. If they differ a lot, the intrinsic reward signal will be high. If the states have been visited many times, the forward model will be gradually trained to predict the correct next state embedding, such that the intrinsic reward will also diminish. As a result, ICM can be used to measure the novelty of states. ICM generates intrinsic rewards for novel states to encourage the agent to pursue. The agent can thus be motivated to maintain exploration and may finally hit the true external rewards in sparse reward environments. Since ICM requires both a forward model and an inverse model, we may wonder if there is any other techniques that can generate intrinsic rewards but do not need to use the information of the action performed by the agent. Remember that the forward model and the inverse model in ICM are both function approximators. If we can use a different function approximators to measure the novelty of states, we may remove the need to use the action performed by the agent for generating intrinsic rewards. In last year, an approach called FlowBased Intrinsic Curiosity Module, which was abbreviated as FICM, was presented at IJCAI 2020. In FICM, the novelty estimator is neither a forward model nor an inverse model, but an optical flow estimator. Optical flow is the displacement of pixels between two consecutive images. Optical flow predictor predicts such displacement using convolutional neural networks and has been investigated in the area of computer vision for many years. In this work, the flow predictor was first used as the novelty estimator to generate intrinsic rewards. Given two consecutive states, the flow predictor is expected to estimate the correct optical flow and use the estimated optical flow to warp one of the input states to align with the other. If the flow predictor cannot correctly estimate the optical flow between the two input states, warping and aligning will cause significant errors, which can be used as a measure of the novelty of the input states and generates intrinsic reward signal. If the two states have been visited many times, the flow predictor will be trained well, and thus the intrinsic rewards will be low. By leveraging the property of optical flow, FICM is especially suitable for tasks that take raw images as inputs. In order to estimate the optical flow between two consecutive images, the flow predictor in this work is based on the famous architecture called FlowNet 2.0. FlowNet is a pioneering architecture that was proposed to estimate optical flow using deep neural networks. According to FlowNet, two different designs are possible. The first version concatenates two input images together and directly uses them to predict the optical flow between them. The second version uses different shear weight branches for the two images and fills the extractive features for them to predict the flow. Both of these two versions perform well and are both applicable to FICM. Yes. Now let's move on to discuss another famous approach to generate intrinsic rewards, which is called random network distillation, RND. Before we dive into the details of RND, let's first take a look at the possible sources of prediction errors from function approximators. The prediction errors can be caused by four different reasons. amount of training data, stochasticity, model misspecification, as well as the learning dynamics. The later two reasons are more related to hyperparameter tuning, which is also a very important issue, but is not within the scope of this talk. In this talk, we care more about the stochasticity issue, which may cause the noisy TP problem. As you can see in this figure, if we use a forward model which attempts to predict the embeddings of the next state, it may fail in an environment that contains a TP wall that keeps changing the image frames randomly. In order to address this problem, R&D proposed a method that does not use the forward model in ICM. In random network distillation, instead of using a forward model, it adopts a randomly generated target network. The parameters in this randomly generated target network is fixed and randomly initialized. For each input state, the novelty is measured by comparing the difference between the predictions from a predictor network and the target network. The predictor network is a learnable network. As a result, if the predictor network is able to successfully imitate the behavior of the target network for a state, a low intrinsic reward will be generated. On the other hand, if the predictor network is unable to mimic the behavior of the target network for a state, a high intrinsic reward is generated to encourage the agent to visit that state more. By using this approach, R&D does not require the use of a forward model and thus can alleviate the stochasticity problem. This slide summarizes the difference between next-state prediction and random network distillation. The next-state prediction method is illustrated on the left-hand side, which uses the embedding of the current state and the action performed by the agent to predict the embedding of the next state. The predicted next state embedding is compared against the true one to generate the intrinsic reward. Random network distillation is illustrated on the right-hand side. Differing from the next state prediction method, R&D uses a predictor network to predict the embedding of the certain state from the target network. The difference is used as a measure of novelty to generate the intrinsic rewards. One thing that is noticeable is that for both methods, intrinsic rewards are consumable resources. Therefore, if the agent keeps visiting the same state, the intrinsic rewards will gradually decrease to low values because the predictor networks are both learning. Now let's turn our attention to a more recent exploration technique called Never Give Up, which is a method presented at International Conference on Learning Representation 2020. Never Give Up is designed such that it is especially suitable for solving hard exploration games. More specifically, it is able to perform well in an Atari game Pitfall without the help of demonstrations or handcrafted features. In the algorithm of Never Give Up, it jointly learns a family of policies with various degrees of exploratory behaviors. Never Give Up, or simply called NGU, proposes a different intrinsic reward mechanism that consists of a lifelong part and an episodic part. The lifelong part encourages the agent to visit as many states as possible during the training phase and will last across episodes. On the other hand, the episodic part encourages the agent to explore number states within a single episode. As a result, this method has the name Never Give Up because the episodic intrinsic rewards will always exist for different episodes. To be more specific, this figure shows the framework of NGU. NGU combines the intrinsic reward with the external reward by a parameter beta. It similarly takes two consecutive states as inputs and uses an embedding network to encode the input states to representations. For the lifelong novelty part, NGU uses random distillation network to generate a parameter alpha that is used to scale the episodic novelty. For the episodic novelty part, NGU keeps storing the embeddings of state within an episode in an episodic memory. When a new state embedding comes in, it is then compared with the contents in the memory to check if it is similar to them. If the new state embedding is very similar to the contents stored in the memory, the episodic novelty will be low. However, if it is quite different from the contents of the memory, a high intrinsic reward will be generated, because it implies that a novel state may have been found. By integrating the lifelong novelty and the episodic novelty, NGU is able to achieve outstanding scores in many Atari games. Besides NGU, let's also take a look at a technique called Go Explorer, which is also a famous method published by the Nature magazine. Go Explorer consists of two phases. In the first phase, Go Explorer contains two operations, Go and Explore. The objective of the first phase is to find interesting novel cells, where the definitions of novel cells in this paper are any new interesting states that have not been found or may lead to higher return. In the Go Explorer framework, such novel cells are stored in an archive with the full trajectory, the length of it, as well as the total reward received from the trajectory. This allows the agent to revisit the formerly explored states and restart from those states easily. As a result, the Go operation first moves the agent to one of the cells using some heuristics from the archive and go there. The Explorer operation is then applied such that the agent starts exploring new novel states from that frontier. As long as any new novel cells are discovered, they are then stored into the archive, and the entire process restarts again and again until the MDP is solved. The second phase then uses the trajectories collected from phase 1 to improve the robustness of the agent. More specifically, it uses imitation learning to learn from the best trajectory experience to update policy. Meanwhile, stochasticity is added during phase 2. At the end, let's take a look at another exploration technique called Bootstrap DQ1 and Mixture Bootstrap DQ1. Bootstrap DQ1 is based on the concept of ensemble learning, which uses an ensemble of models to predict the final results together. In Bootstrap DQ1, a shared convolutional neural network is used to extract features from input images. After the input features are extracted, it then uses multiple bootstrap heads to predict value estimates. These bootstrap heads are initialized independently, which means that they have different random states and may lead to different learning results during the training process. In each episode of the training phase, one of the bootstrap heads is randomly selected and is then used for the entire episode. After the training process, the policy of the agent is determined by the bootstrap heads using a majority voting mechanism. Since different bootstrap heads are initialized independently and undergo different learning processes, we can assume that the behaviors of them may be different. Therefore, such different behaviors may cause the agent to explore different states and thus encourage the exploration behavior. In this year, an enhanced version of Bootstrap DQ1 is proposed, and it's called Mixture Bootstrap DQ1, or simply MBDQ1. The architecture of MBDQ1 is basically the same as the original Bootstrap DQ1. However, in MBDQ1, different Bootstrap heads further uses different numbers of step returns for training the value functions. Therefore, some Bootstrap heads may use one step return, while some other Bootstrap heads may use multiple step returns. This way, the learning processes of the value functions of different Bootstrap heads are further diversified, allowing the agent to explore more states in the environment. MBDQ1 was just presented at International Conference on Machine Learning Workshop this year. Let's move on to our final section, which is about how to apply reinforcement learning concepts to robotics. We will have several robotic cases to discuss and present to you. We will begin our discussion with inverse dynamics model, which is the same thing as the inverse model used in ICM we just talked about before. Given two consecutive states, the inverse model predicts the action between them. So why the inverse dynamics model is important? Because it is useful for robotic applications. This image is obtained from a related paper from International Conference on Robotics and Automation. Given a desired motion, say a list of consecutive images, a robot can accomplish this motion by recursively applying the inverse dynamics model to obtain an action sequence. However, how do we obtain an inverse dynamics model? We can approximate the inverse dynamics model by a deep neural network. There are two common approaches for training an inverse dynamics model. One way is to use human demonstration. This approach can easily collect high-quality data. However, the downside is the need for human efforts. Another approach is using random exploration. This exploration requires no human effort, but the quality of data is already low. It's very difficult for a random explorer to perform complex motions. The lack of complex motions in the dataset may impair the quality of the inverse dynamics model. To this end, we would like to show that we can use adversarial active exploration. The method is very interesting. It trains a reinforcement learning agent. In order to achieve this objective, we can actually use an adversarial training approach to actively collect data samples for training the inverse dynamics model. In this adversarial training approach, a reinforcement learning agent is used to search for and collect complex motions for the inverse dynamics model. This slide shows the adversarial approach for training the inverse dynamics model. It consists of a reinforcement learning agent P and an inverse dynamics model I. The two models compete with each other and learn together to become better and better. The responsibility of the reinforcement learning agent is to explore the environment and collect data samples for training the inverse dynamics model. On the other hand, the inverse dynamics model uses the data samples collected by the reinforcement learning agent to train itself and generates intrinsic rewards if there are any prediction errors. The reinforcement learning agent is encouraged to increase the inverse dynamics model prediction errors. The reinforcement learning agent is encouraged to increase the inverse dynamics model prediction errors by collecting difficult samples in the environment. The inverse dynamics model attempts to decrease its prediction errors by gradient descent. This kind of competitive relationship creates a natural curriculum to continually improve both sides. Therefore, we will get the number of complex motions in the dataset. Under this setting, no human effort is required. In this video, we will see how the agent collects non-trivial data. The black box is the object we are interested in, and the red point is the target in this case. As you can see, the robot intentionally plays with the object, which leads to tons of complex interactions. Those complex interactions can be used to train the inverse dynamics model and improve its performance. So now, let's switch our attention to another simple question. How do we train a real robot? Here is a video from Google research team at 2016. In this paper, they proposed a large-scale training method to train the robotic arms to grab items in the real world. It is really awesome, and they achieved great performance. However, there are still several things worth to be noticed. The first one is the time consumption. In this paper, the researchers state that they spent over 3,000 hours for practicing. That is roughly equal to 2 months, and it's overly long for common users. The second one is danger. As you can imagine, training the robot or autonomous car in the real world is really unsafe. It may also cause potential damages. For example, what if the robot bumps into the wall or falls into water? Those conditions are really dangerous and we always want to avoid. The final one is the cost. Regular people do not necessarily have enough budget to buy lots of robotic arms, unless you are really rich. So in order to overcome this problem, we would like to discuss another way to deal with this issue. This method is called virtual-to-real transfer learning. So to introduce this concept, first I would like to show a modular architecture which allows us to train the agents in simulators. Then we can transfer the agent into the real world directly without use any other human efforts or fine-tuning. After the training phase, the reinforcement learning agent can be transferred to a real robot and perform well in the real world. So let's take a look of the advantages of virtual-to-real transfer. There are several advantages to train robots in the virtual world: safety, speed, and money saving. Training a robot in a simulator is safer than training it in the real world. In the simulated environments, the robot can perform whatever actions, try any kinds of exploration behaviors, without the need of worrying about hurting people and causing any damages. Training in virtual environments is also much safer and faster than training in the real world. Imagine that you are training a robotic arm. In the real world, it takes several seconds to complete a grasp operation. However, in the virtual world, it may just need milliseconds. In addition, virtual worlds allow us to use parallel training, which can further accelerate the training speed. Finally, training robots in the virtual world is cost efficient, since we don't really need to purchase lots of real robots for collecting physical training data samples. However, if we want to train a robot in virtual worlds and transfer the policy learned to the real world, there is the problem we need to overcome, which is called the reality gap. The reality gap means the difference between the virtual worlds and the real worlds. As you can see in this figure, the right-hand side is the virtual world, and the left-hand side is the real world. They differ in light, texture, shape, and shadow, making the policy learned unable to directly transfer to the real world. More specifically, the robot is familiar with the virtual environment on the right-hand side and feels strange with the real world on the left-hand side. So how do we solve this problem? The problem can be addressed by using a concept of mid-level representation. In this talk, the mid-level representation is based on semantic segmentation. Semantic segmentation performs pixel label predictions for both the virtual and real worlds. Through the use of such a mid-level representation, the robot directly learns from the semantic segmentations in virtual worlds. In the real world, the learned policy can be directly transferred as long as the representation of semantic segmentation is similar. So, how do we implement the concept we just discussed? Here is the software architecture. In this architecture, there are three modules in it: a perception module, a control policy module, and a visual guidance module. The perception module is located on the top left corner and is responsible for encoding raw images to mid-level representations. That is semantic segmentation. On the bottom left corner, there is a control policy module, which is implemented as an A3C reinforcement learning agent. The agent takes semantic segmentation as its input and learns a policy to perform actions. The last one is the visual guidance module on the right-hand side. The visual guidance module allows us to change the target through high-level commands by simply changing the segmentation colors here. Let's now move on to the details of the perception module. There are two paths here. One is for execution in the real world, and the other is for training in the virtual environments. In virtual environments, we use segmentation shader to obtain the semantic segmentation for training usage. On the other hand, in the real world, the segmentation model can be implemented by the state-of-the-art segmentation network such as DeepLab, ICNet, and PSPNet. This virtual-to-real concept has been proven very effective for robot training and has received the grand prize at NVIDIA Jetson Developer Challenge in 2018. By the use of semantic segmentation, training a reinforcement learning policy in virtual worlds and transfer it to the real world becomes much more practical and easier for robots. So, how can we create such virtual environments for training reinforcement learning policies? There are several available tools that we can use to create such environments. Unity is one of such tools, which have many available building blocks to allow us to create different environments. Unity is also compatible with the library called ML Agent. ML Agent supports interactions of reinforcement learning algorithms with Unity environments. By using them together, we can easily train our policies in virtual worlds. This is a simple example environment created by Unity for training an agent. The agent can move around in this environment, learn to avoid obstacles such as the blue blocks, and approach the goal highlighted in green to obtain rewards. Let's take a look of another example. This is a simple example showing that A3C agents can learn an effective policy to turn right and approach the goal without hitting the boundaries of the road. Let's take a look of a more complex task in simulated environment. The video on the left-hand side shows an obstacle avoidance task, while the video on the right-hand side shows a target following task. For the target following task, the agent is required to follow a person in front of it. If the agent fails to follow the target or loses it, the agent receives 0 reward. If the agent is able to keep following the person, it receives some reward every time step. In the obstacle avoidance task, the goal of the agent is keep moving forward while avoiding collision with the obstacles. If a collision event occurs, the agent receives -1 reward and restart the episode. Otherwise, no reward is given to the agent. So as you can see in the videos, one of the advantages of training agents in virtual worlds is that we can generate any kinds of visual representations for the agent, such as semantic segmentation, depth map, and random texture rendering. In order to ensure that the agent can learn an effective policy in virtual worlds without overfitting to certain environments, an effective trick is to use multiple environments. During the training phase, a random environment is chosen, and the agent is put into that environment in a random location. By doing so, the policy learned by the agent can be more general and more applicable to the real world. Here are some simple environments that can be used for evaluation. These environments are all created by Unity, covering scenes such as indoor office, outdoor town, living room, and an indoor space for the target following task. Now let's demonstrate the policies transferred to the real robot. The policies learned in the virtual worlds include target following and obstacle avoidance. The robot used for demonstration is a Segway platform. Another thing we want to ask is, besides obstacle avoidance and target following, can we apply the virtual to real concept to navigation tasks? The answer is yes. Since semantic segmentation already contains semantic meanings, we can definitely extend the concept of visual guidance to something called a virtual guide. As shown in this figure, the virtual guide is rendered as a two-dimensional yellow ball. The agent can be trained in virtual worlds to chase the virtual guide and obtain rewards. In the real world, the virtual guide can be rendered on the semantic segmentation perceived by the robotic agent. As depicted in the clip here, the robot will feel like there are virtual yellow balls placed in front of it. Since the robot is trained to chase those yellow balls, the robot will follow the guidance of those virtual balls towards some waypoints or destinations. Then we may want to ask, how do we place those virtual balls? The answer is to rely on a technique called simultaneous localization and mapping, which is also called SLAM. SLAM can help the robot to understand its location and orientation without the need of any GPS or motion sensor. This is the overall architecture for combining the concepts of virtual to real transfer, SLAM, and reinforcement learning. The input image of the robot is first forwarded to two modules, the perception module and the localization module. These two modules derive the semantic segmentation as well as the location and orientation of the robot. Then, this information is sent to a planner module to derive the optimum path to the destination. Waypoints will be placed along the way such that virtual balls will be rendered on the semantic segmentation perceived by the robot accordingly. Finally, the control policy module controls the robot to follow the virtual guides and proceed to the destination without hitting any obstacles. This work has received the second place of the award from NVIDIA AI at the Edge Challenge in 2020. Here's a demonstration of using virtual to real transfer, virtual guide, SLAM, and reinforcement learning to perform navigation tasks. Finally, I would like to give a summary. In today's talk, we have discussed the fundamental concepts of reinforcement learning and have introduced the concept of deep reinforcement learning. We have explained the importance of exploration and discussed several representative exploration techniques. We have finally discussed how reinforcement learning can be applied to robotic applications and demonstrate how a policy can be trained in virtual worlds and transferred to the real world. So thank you for your attention. If you have any questions, please feel free to ask.
Okay, so we thank Professor Lee for his fascinating talk. So now the Q&A session started. So if you have any question, feel free to type in the chat box, and then Professor Lee will first answer the question they already show in the chat box.
Okay, so can you hear me? Hello. I just want to make sure that you can hear my voice.
Yes.
Oh, okay. So, okay, now I will begin answering the question. So I will start from the beginning. The first question is, are we just using the hidden layers? So we only use the feature map? So for this question, I would just like to answer as follows. So when we design a network, we always need something to extract features from the state or observations. So that is the first stage. So this is the same as computer vision networks. So in reinforcement learning, we also use some feature encoding networks. This can be fully connected layers or computational layers. It depends on what task we are doing. For example, if we take images as inputs, then we may use computational layers to encode the input images to some kind of features. And these kind of features can be used for any kind of purposes. Like computer vision, we have a field called transfer learning. And this concept can also be used in reinforcement learning as well. So after extracting features from the input images, we can use the extracted features to derive the policy for the agent. For example, the output of the neural network can be the probability of the actions. So we use the encoded features and pass it to several fully connected layers, for example. Then those layers can tell us the probability of which action is more likely to perform. So this is how we use the hidden layers. So I hope this answers your question. This is the first one. And the second question is, if we're gonna use deep reinforcement learning, we need a label data for the network, right? The answer is no, because for reinforcement learning, there is no label data actually. This is not the same as computer vision tests. So in most of the computer vision texts, we have a data set which contains data and labels. But for reinforcement learning, we basically use an agent to interact with the environment. The environment only tells us state transitions and the rewards given to the agent. So we only have state transition and the reward. And we may either use policy learning or on policy learning to leverage those state transitions and rewards to derive our policy. So there is no ground truth labels for reinforcement learning agents to learn. So this is why we need to use the target network in DQ1. So because in DQ1, the target network is updated for a certain period of time. So if we are not updating the target network too frequently, the target network will be stable for a while. Then that stable target network can be used as a reference for the agent to learn a better value function approximator. So the answer for this question is no. There's no label data. There's no one can tell the agent what's the correct way to perform in the environment. There are multiple ways to do in the environment, but we can only determine if the policy learned by the agent is good or bad. We can use the performance, for example, the scores achieved by the agent to determine if this policy is good or bad, but we do not have any label data for the agent. So that is for the second question. And the third question is there any link for the slides? I guess the answer is yes. The slides will be open for download afterward. So, and along with the video, I guess the video will be put on YouTube and the slide will be downloadable. So don't worry about it. You can take a look of it anytime after the machine learning summer school. So the next question is, during the MDP, does the agent change the environment when interacting with it, or does the environment remain the same despite interaction? For this question, I would say for most cases, the environment is not changing because MDP basically depends on the environment. And we basically use the MDP to tell us the state transitions and the rewards when we transit from one state to the other. So the environment is not changing. Otherwise, we cannot derive the correct value or the correct policy because a changing environment will make the agent very confused and the value may be fluctuating. So in most cases, I would say in most cases, the environment won't change. But there's some new research domain. There are some new research domains that allows the environment to change a little bit, or we can deploy the agent to different environments to test the generalizability or robustness to the changes. So that is more advanced areas for reinforcement learning. But for most cases, the environment are not changing. For example, if we are playing Atari games or Mujoko, the environment will be basically the same. So yes, no. So the answer is no. The environments are not changing. Okay, I just saw a question just posted. If the environment changes, it is partial observable MDP. Partial observable MDP is also called POMDP. So for POMDP, the agent actually observes a little bit area of the environment. So the agent cannot observe the full environment state. That is POMDP. And POMDP is POMDP is applicable to most cases because in most environments, the agent cannot observe the full states. It can only observe some of the states. For example, if we are controlling a robot, the only input to the robot is the camera and maybe some other sensors. But the camera cannot observe all the environment details. So this is a pure MDP problem. So if we want to solve the pure MDP problem, we can use several ways, such as we can use a recurrent neural network to record the history of the interactions. We can do something like that. And we can also use some more advanced styles like LSTM or GRU. So those kind of network architectures can be used to partially to kind of solving POMDP. So this is for this question. The next question is it possible to just select what to learn or replay from the experience buffer? Yes. Yes, the answer is yes. So if we have an experience replay buffer, we can choose what data samples we want to use to update the agent's policy or value. So because the experience buffer is actually maintained by the agent and the data inside it is generated by the agent, we can, of course, we can definitely select data. We can select a batch from the experience replay buffer and use that batch to update the agent. And what batch, what data to be selected into the batch can depends on the selection mechanism. For example, there is a technique proposed several years ago called prioritized experience replay buffer. In prioritized experience replay buffer, we actually samples experience that has higher temporal difference error. So higher temporal difference error means that the value estimates for those samples are larger than the others. So in other words, we in prioritized experience replay buffer, we select samples that has higher prediction errors and use those samples to update the agent first. So yes, we can give some priority to the data samples in the experience replay buffer and use those samples to update the agent. And this may make the learning process faster and more efficient. The concept of prioritized experience replay buffer has been used for a long time, and it is still being used in most recent deep reinforcement learning methods. So that is for this question. The next one is, let me see, what's the next one? The next one is if two or all choices is equally rewarding, how will the agent react? Will it keep deciding without doing anything, select choice at random or something else? If two choices are equally rewarding, then the agent will react depending on the policy of it. So because the agent can decide what to do depends on its policy approximator or depends on the value estimator if we do QLearning based reinforcement learning. So for policy-based reinforcement learning, the agent has to predict probabilities for different actions. And based on those probabilities, we sample an action to perform. So if two choices looks equally rewarding, then the agent will just sample one of the action depends on its probability predictions. And if we use value-based reinforcement learning, then we actually transform the value function by some softmax function to make it a Boltzmann equation and use that equation to sample the probability of the actions. And the same, we use some kind of probability to sample actions so to allow the agent to perform. So so it really depends on the policy. This is for this question. Let me follow up to see the next one. Where is the embedding in this graph for slide page 38? 38 is, let me take a look. Oh, page 38 is the curiosity-driven exploration. And the question is, where is the embedding in this graph? So the embedding in this graph means phi of st. So given an input image st, we use an encoding network to extract features from this input state. And the extractive features is also called an embedding. And this embedding is represented as phi of st. So this is the embedding in this graph. And we actually use the same embedding network to encode the input states st and st plus 1 to two embeddings, and use these two embeddings to guess the action between it and by the inverse model. And the embedding is also used to fit into the forward model to predict the next state embedding. And we use the predicted next state embedding to compare with the ground truth next state embedding to guess, to see if they are similar. If they are similar, it means that the agent is already very familiar with this state. Otherwise, if they are very different, then it means the agent has not seen this state for many times. Then we can use the difference to derive intrinsic reward to motivate the agent to visit those states more. So yeah, this is the answer to this question. Okay, so the next question is, for the virtual to real deep reinforcement learning, is it standard practice for parallel training to test several exploration strategies in the cases where multiple strategies would make sense? The answer would be yes, but I would like to say, when we do virtual to real deep reinforcement learning, the virtual worlds are actually created by ourselves. So we can deploy the agents. We can actually deploy multiple agents in the environments and use those agents to collect data samples for us to update the policy or the value function. And for different agents in the virtual environments, we can definitely use different strategies, different exploration strategies to encourage them to perform different behaviors. And this method has been used has already been used in many different reinforcement learning techniques. For example, in A3C, different agents can have different extent of epsilon value. Remember, epsilon greedy exploration means that you have a very small probability that the agent will take a different action other than the policy predicted. So, of course, you can have different values of epsilon for different agents. And we can deploy multiple agents in virtual environment to collect different experiences and use those experiences to update the policy of the agent. Okay, so the next one is, what's your opinion on using reinforcement learning in computer vision tasks, such as tracking? Okay, so when we talk about tracking, it really depends on the scene of the environment. So if we are tracking the same person, then it may be possible. But if we are tracking multiple persons and the number of people in the observation space are dynamic or keep changing, then it may not be an easy job, because if we cannot if there's a dynamic number of people appearing in the environments or in the observation of the agent, it means that the MDP is not static. So if we want to use reinforcement learning to track people in an observation, it would be challenging because the number of people will not be the same, and the people appearing in the observation will also not be the same. Then it will make the tracking task very challenging. So the next question is, you mentioned different reinforcement learning and deep reinforcement learning algorithms. Could you talk about which algorithm more closely resemble human behavior, or how they each resemble to human behavior under different circumstances? Sometimes humans may even act suboptimally. Do you have any recommendations for modeling that? Another question is, when a human learns to drive a car, they don't use reinforcement learning, can't afford errors. So how is this done? Okay, so actually there are many questions in this one, but I will answer one by one. So the first one is, could you talk about which algorithm more closely resemble human behavior? Actually, I would like to say all of these algorithms are invented based on what we think about human beings may do, because for value-based reinforcement learning, we need to learn a value function. And for human beings, we also have some kind of values in our mind. For example, if we are going out for lunch, then we may have some preference to go to some restaurants. It really depends on your experiences. So if you have been to some restaurant and you feel that it was really delicious, then this experience may motivate you to go to that restaurant more often. But if you have experienced, if you had a very bad experience for some restaurant, then that can be viewed as a negative reward, and you may want to go to that restaurant again. So in your mind, you are actually building up a value function for the restaurants. So value-based reinforcement learning is also very similar to what human is doing. And policy-based reinforcement learning is more like your behavior, or it's more like your behavior, or is more like what you intentionally want to do. So for some people, you may just say, oh, this morning I just want to go out, or I just want to work. So you have some kind of preference. So you basically learn what kind of behavior is better for you. So this is more like your you prefer to do something. So policy-based reinforcement learning is more like your preference. You will learn a better preference to learn to achieve a better reward total return. But for value-based reinforcement learning, you are actually learning values for different behaviors. So these two methods are both derived from human behavior. So I would like to say that. The second one is, sometimes human may even act suboptimally. So yes, agents also do behaviors suboptimally. So like we have discussed in our talk, we use exploration methodologies to motivate agents to do some suboptimal actions. So for example, the simplest one is Epsilon greedy. In Epsilon greedy exploration method, the agent has a very small probability to do the actions that the policy does not want it to do. So those actions are maybe suboptimal because the policy wants you to go. For example, the policy wants you to go right, but if you always go right, then you can not have any chances to try other actions like go left or go forward. So if you go left and go forward, maybe you can get even higher reward, but you don't know. So exploration actually motivates agents to do something that may look suboptimally, but you may have some chances to get higher reward than the current one. So this is actually the same as human beings. We just motivate the agent to do something that looks suboptimal, but it may eventually have some chances to become even better than the current one. So the final question, the last question is, another question is, when human learns to drive a car, they don't use reinforcement learning. Yes, when human drive a car, they don't use reinforcement learning, but human beings do have some rewards, like what we have. We may have some intrinsic rewards. For example, when we drive a car, if we can drive very good or successfully for your first time, you may feel very happy. And this feeling is a kind of intrinsic reward because you feel happy, so you want to do more. But if you just hit something, like if you hit a pedestrian or hit the curb, then you damage your car, you feel very sad, then you may not want to do that again. So this is very similar to a negative reward. So the mechanism is very similar to human beings. Human beings also learn to do something based on your internal rewards. So internal reward is very similar to the meaning of rewards in reinforcement learning. So we also do the same thing. You do something, you feel happy or you feel bad, and basically you base your experience to shape your behavior, and next time you will do better. So this is the same as human beings. The next one is this model able to navigate under low light environment? The answer is it really depends on the perception model, because if you want to take inputs from low light environments, you need to adjust, you need to train a perception model to be able to predict things under low light environments. So usually you predict semantic segmentations under regular sunlight environments, maybe at mid-noon, but under low light environments, you need to make your perception model more robust. Maybe you need to do some data augmentation or prepare more training data for your perception model. So this is more like a question related to computer vision. So how do we use computer vision to extract more robust features for our agent to use? So for intelligent robotics, we basically have a perception module and control module, and the reinforcement learning agent is for the control policy module. So the control policy module receives input from the perception module, and the input can be any raw image or the semantic segmentation or the depths or any other things. And it takes whatever the perception module gives it to it, and it predicts actions. So if the perception module cannot process the input images well, then the agent may not perform well. So we need to make the perception module more robust and general. So this is more related to computer vision issues. And we need to have some ways to train a more robust model, like data augmentation or collect more useful data samples on the low light, or you can do some domain adaptation. Domain adaptation means that you can use generative models to transform the low light environment images to the images that the agent is already trained for. So this is the answer to this question. What's your advice on policy reward shaping? So policy reward shaping it really depends on the task. So sometimes you may want the reward overly high or overly low, so you need to do some adjustments and to generate suitable reward within some range. It really depends on the task. So yeah, I cannot give a concrete answer for this one because it varies task by task. So there's a question: if the events in probability space can be partially observable, and some of the environment changes we observe a projection of an even I'm not pretty sure about this question, POMDP. So maybe the question about POMDP can be more specific, and I can answer it offline because I'm not pretty sure about the question. So what's the opinion about the high computational cost of deep reinforcement learning? Google just released revisit Rainbow about this issue. What's your opinion about the future cost-effective growth of deep reinforcement learning? Okay, yeah, about the cost, computational cost of deep reinforcement learning. Actually, we also have a paper this year at International Conference on Robotics and Automation about reducing the computational cost. So how do we reduce the computational cost? I would just like to share my method. Actually, our method is that when you deploy an agent in an environment, you do not always need to perform. You do not always need to use a very complex deep reinforcement learning model. In some cases, you only need to use simple models, and in some cases, you need to use complex models. For example, if you are driving on a straight road, like if you are driving in the Midwest, in the desert of United States, very straight, the road is very straight, then you don't need to use a very complicated model to do this task, because the agent just need to control the car to be within the range of the road. So you can use a simpler model to drive under this scenario. But if you are driving for very complex things, like you are driving in the mountain or in a city, in a very busy city, like you are driving in the San Francisco or New York, then the agent has to be very careful about the pedestrians and the other cars. So under such scenario, you may need to use a very complicated model. So the way to reduce the computational cost that we have proposed is that we can have a master model. The master model will decide under the current scenario, current observation, we want to use a complex model, or we want to use a simpler model. The master model will decide. So the master model will take an image as its input and say, okay, the current observation looks like a straight road, then we can use a very simple model because you don't need to handle complex scenarios. There will not be other cars driving from your side, so you can just use a simple model to control the car. But if the master model feels like, oh, there's a traffic lights, there are other cars close by, it's very dangerous, then in under this scenario, you may need to use a more complicated model. So we are just using the master model to balance between simple model and complex models, so we can switch between them. So by using this method, we can reduce the computational cost, because you do not always need to use a very complicated model for all the scenarios. In some cases, you just need to use a simple model. Then by using simple models, you can reduce most of the costs. So the next question is, do you have a preference, one, any in why policy gradients or QLearning? Do you have preference? So I guess this is a question for my preference. For us, we usually use QLearning based reinforcement learning or actor-critic, because for QLearning based reinforcement learning, the recent trend is that people are extending QLearning reinforcement learning to distributional Q network. Distributional means that instead of directly learning the expected return of a state, we actually learn the distribution of that expected return. This is a more complicated task. but it's very effective and useful. So for many of the recent techniques, people are using distributional QLearning to achieve even better results than expected return-based QLearning. So if you are interested in this area, you can take a look at distributional reinforcement learning. The keyword is distributional reinforcement learning. In this area, people try to learn the distribution of Q values, and it's very effective. What's your opinion on choosing an exploration strategy for a particular problem? How do we consider most? Exploration strategy, okay, my opinion is that if you can try the most simplest one first. For example, the most simplest one is Epsilon greedy. So anytime when we want to do exploration, we try the simplest one first because it's very easy to implement. You just add a very small probability that the agent will behave differently. So try Epsilon greedy first. And if that doesn't work, or if you know that the external reward is very sparse, then you can use curiosity-driven exploration method. Try to add some intrinsic reward. If you feel that it's very difficult to get any external reward, then you can use curiosity-driven. I guess I have answered all the questions. So I will give control to the host. So thank you for attending. Thank you for attending this talk.
Okay. Yeah. So thank Professor Lee for the questions, and thank you all for attending this session.